Okay, so good afternoon, everyone. So today we're going to do a short tutorial on using svFSI, doing fluid structure interaction simulations using svFSI. I'm going to share my screen. All right. So here is some of the basic introduction to the code. So basically, we have the code and the documentation related to that, related to the fluid structure interaction. So you have a couple of, if you go to the SimVascular web page and SimVascular documentation, here you can find a guide for svFSI, so which is here. So this one was created a couple of years ago, but it's still kind of a good start for people who are just launching into fluid structure interaction simulations, and especially using a technique called arbitrary Lagrangian Eulerian. So in general, in SimVascular, you can do you can do fluid structure interaction using two methods. So in the first method, which is called the coupled momentum method, that's already part of SV solver. So that one is for small strains, small displacements, and assumes linearity. However, if you want to do large strain, large deformation fluid structure interaction with complex material models, then you'll have to use arbitrary Lagrangian Eulerian formulation. And this tutorial here goes through some of the basics. In addition, I will also kind of guide you to the SimCardio project. So there is a SimCardio guide here. So here you'll see a little bit of introduction to the multiphysics finite element code that we are going to be using today to do the FSI. So here, basically, it's svFSI, the multiphysics finite element solver. And there are like several different features of the code. You can directly install it using the installers from the SimTK site. So here is the SimTK website, and if you go to downloads, you'll be able to see the svFSI executables. But we also recommend you to download the source code, which is on GitHub, and compile it in order to get the best features, the most updated features of the because we are time and again we are adding some new stuff here. So you'll have access to the latest version. So there's a good README file here. So it kind of introduces you to the code. There's some instructions to how to install it for dependencies, quick build. And if you want to invoke Trilinos, which is a very large linear algebra, so linear solver library, so you can couple svFSI to that. And there are some documentation. There's some documentation related to features of the code, like the type of material models, non-Newtonian flows, the type of viscosity models for non-Newtonian fluid dynamics, cardiac electrophysiology models, etc. And then there are also some instructions on how to install, say, the dependencies in great detail. So these are all some of the installation instructions on building all the dependencies from source. So now you can therefore install, and those install instructions include both for Linux as well as the Mac OS. On top of it, actually svFSI, so we kind of shared a number of examples here that people could start off with to get good experience on how to use the code. So there is a master input file here. It's called svFSI test repository. And so there are like a bunch of tests here which are organized based on the physics. So like I said, it's a multi-physics solver. So you have a diffusion, you have linear elasticity, Stokes flow, fluid flow, Navier-Stokes equations, the nonlinear solid dynamics using two different types of formulations. One is a pure struct, is a pure displacement-based formulation, and you have the U-struct, which involves a mixed formulation using velocity and pressure and test functions as the unknowns. You also have FSI examples, which we are going to go through in shortly. And you also have a little bit about some examples about cardiac electrophysiology and shell mechanics. So the master input file kind of gives you a great detail of all this. So basically, svFSI needs a script file. It needs an input file, the executable that you build. So it needs an input file, and that's a script. And you have to so this master input file kind of gives you lots of details about the commands and the format that goes into the script. So essentially, it kind of, so we'll go a little bit into some of these details, but broadly, you have three different sections in this input file. So one is where you specify some of the general simulation parameters like time step, for output control, spatial dimension of the problem, and then you provide information related to the mesh where you load all your mesh details. If you have any fibers, you want to load them. If you have any multiple domains where you're prescribing different material properties, you want to include them within the mesh information. And then you have the equations. So where you define your equations that you want to solve, and you define your solver properties, solver tolerance parameters, solver parameters, linear solver parameters, non-linear solver parameters, boundary conditions, etc. So this is a test repository. I will also encourage people to kind of go through a little bit about the mesh generation for FSI. So one of the challenges with FSI is you want to have a mesh that's conforming. So svFSI, the code that we use, it uses a monolithic coupling, which means that if I can explain that, maybe taking an example here. So let me open a Paraview window, and here I'm going to load a mesh. Let's say this is my fluid mesh. So here is my fluid mesh, which I'm going to show with edges. And then I'm going to load a wall, the tissue mesh. And let me load the, so this is your wall mesh. So the thing with svFSI is that because it uses a monolithic coupling, you want to make sure that at the fluid solid interface, so you want to have a nodal conformation. So the nodes, nodal topology, the mesh topology at the interface should match between the fluid side and also the solid side. So here, I think there's a good tutorial here on how to create this kind of meshes. So I'd encourage you all to first go through that before working on setting up a problem. So let's say now that we have gone through some of the preliminaries, we have created a mesh where we have a nodal conformation, nodal conforming between the fluid and the solid interface domains. And now we want to do the fluid structure interaction simulation. So I would encourage you to, again, go into these examples. So you have the FSI examples, and today we're going to go into the ALE simulations and the pipe case. So within pipe, there's the input file here. So I'm going to use the same thing, but locally in my folder structure. So here is the input file. So if I open that, this is what I'm going to see. So this input file, like I introduced earlier, so basically you have three parts. So initially you have the general simulation parameters. So here you define your spatial dimension of the problem. You set the number of time steps, the time step size. Again, people can use the master input file as a reference here to understand what each command actually means and some of the formatting requirements. So for instance, the colon here is a separator between the command the code looks for and the value of that particular command. And so there are kind of other specifications too, which you can gather from the master input file. But essentially, these are some of, and so these are some of the general simulation parameters. So here is a little bit about the output control, because we want to visualize the results in BTK format so that you can open them in Paraview. So this is that part. And then we load the mesh information. So for doing fluid structure interaction simulations, you need one mesh. So using add mesh, this is the add mesh section. So this is for the fluid part, that is the lumen here. And then you have another add mesh section, which represents the wall. There's the arterial tissue. And you load the volumetric mesh, the VTO file, and then you also load all the faces. And let's say we define this domain, we'll come back to this domain later. But for time being, let's say that we define this domain where we define the fluid parameters as one value. Similarly, for wall, we define another domain. Now, one thing that we have to do for FSI simulations is we have to do a projection, because we don't want to duplicate the storage. For example, the lumen wall, which is the outer wall of the fluid region, and the wall inner, which represents the inner wall of the wall region, the tissue region. So they both are actually one and the same. So basically, you know, in order to avoid any memory duplicacy, but also, excuse me, to retain the monolithic coupling where we are applying the kinematic and dynamic boundary conditions at the interface. So we have to do this projection step. This is something that you don't do for any other simulations, let's say fluid simulation or solid simulation. But for the FSI simulation, you need to project the wall inner layer from the lumen wall. So then the code kind of treats them. The code will have internally, it has a mechanism to know that both these surfaces are essentially one and the same. And this is the reason why we need to make sure that we have a nodal correspondence between these two. So that means that the physical coordinates should be very close to each other. It's even better if they're exact, but if they're, as long as they're close with respect to some projection tolerance, you should be able to get the projection right. So then we have the third part, which is the equations. So in the equations, now we specify this to be an FSI equation. So you have other physics, but today we are going to talk about FSI. So here, initially we said a little bit about, forget about the coupling for now. Well, so the coupling kind of in a multi-system equations. So let's say if you have multiple equations, for FSI, we always need to have two equations. So one equation is the FSI, and the second equation, I'm going to jump ahead here and show you that we have to have another equation, which is a mesh equation. So the mesh equation is where your as your FSI, as your fluid and solid interface is kind of deforming as the fluid structure interaction is going on in the process, then what happens is your fluid mesh also needs to deform in order to conform to the interface. The interface is getting displaced. Now, as the interface gets displaced, your fluid mesh also needs to be rearranged. So that's why we kind of solve a mesh equation. Now, this mesh equation, remember, this is only for the fluid domain. You don't solve this mesh equation in the solid domain. You only solve this mesh equation in the fluid domain. So the arbitrary Lagrangian Eulerian is with respect to the flow. So the fluid domain behaves as Eulerian when you're doing the fluid structure interaction simulation, that is FSI equation, and it behaves as a Lagrangian when you're solving the mesh equation. So that's why it's called ALE. So anyway, so basically you have these two equations. So because we have a two equation or in any multi equation system, you need to define a parameter called coupling. So that means the solver will now make sure, so this is a logical parameter, so you can either set it to 1 or true or false or 0. So this coupling makes sure that both the equations, the solver kind of handles the convergence, both the equations are tied to each other, which means that both the equations have to converge simultaneously. That's the thing that the solver makes sure of. And so these are the nonlinear solver settings. You have the minimum maximum iterations, the tolerance for the nonlinear solver convergence. And then we provide the domain properties. So we have a fluid domain where we say that, okay, in this domain, we are solving a fluid equation. We define the density for the fluid. We define the viscosity. It's a constant here, but you can also define non-Newtonian viscosity model here. And then we also have a backflow stabilization coefficient. On the other hand, for the structure side, you have to define the other domain. So this domain one is struct. So in the struct, we are solving a solid nonlinear solid mechanics equation. We can define the constitutive model. So this is the isochoric part, so which is a Newtonian. So that's why we also need to define a dilational penalty model. Here we're using M94. Again, go back to the master input file to get more details on these models. And then we define density, elastic modulus, and Poisson ratio. Now, the struct is a pure displacement-based formulation, but in the same domain, you can quickly change it to a mixed Fermat formulation. So where you can use ustruct, and if you use ustruct, then you have to define these additional stabilization parameters. So we use a stabilized formulation for the ustruct, where you have to define a stabilization coefficient for momentum equation and continuity equation, as shown here. Then you define a little bit about the linear solver parameters. So here we are using the GMRES as the linear solver, and we couple our svFSI with Trilinos ILUT as a preconditioner, and we set some tolerance, linear solver parameters, just tolerance, maximum iteration, and this is a GMRES parameter. This is a Kirillov space dimension. Then we have the output control. So everything is, as you see here, is kind of nested. So you have a command, let's say the linear solver, it takes in the solver name, and then the parameters are defined in nested block. Similarly for output. So these are a spatial output, meaning that these quantities are written to the VTU file, so you can visualize in ParaView. And we are interested in looking at displacement, velocity, and pressure. Now, the mesh also writes out a displacement. So we can define one of the displacements here, for instance, as fs underscore displacement, so that it doesn't overlap with the displacement from the mesh equation. Then you provide boundary conditions. So here we have three phases. One is the inlet, where we are providing a pressure pulse at the inflow, and for the wall, for the FSI system, we want to make sure that the wall is fixed for this particular toy problem. So here are some of the parameters for the wall, for specifying the traditional boundary condition of the wall. So we're kind of trying to fix it, but fix it only in a particular, fix the displacement. and only along a particular direction. So that's where you provide this effective direction. So that means the wall is going to be fixed only along the z direction, whereas it's allowed to move along the x and y direction. So there is in-plane motion on the wall, whereas there on the wall annulus, inlet and outlet annuli, but there is no cross-plane direction displacement. Then we have the mesh equation. Again, similar nonlinear parameter settings, you couple it, and this is the nonlinear parameter settings. You only provide Poisson ratio for the mesh equation, some linear solver parameters, output, and some boundary conditions for the mesh equation. So with this, we should be able to now run the FSI simulation. So I'm gonna show this here quickly. So what happens is, all right, so here is where we have the FSI simulation. So here I have the executable. So I'm pointing this executable. Okay, so I'm creating a link to the executable here. So let's get the side public. All right, so here is our executable, and I'm going to quickly run this using MPI. So I'm using MPI and 8 processes, and just letting it go. So as you can see, it prints out some output here because we have in the initial general parameters, we said that we want to have a verbose output. So it kind of gives you more details as to what it is doing. So it's loading a mesh here, then it loaded all the phase for the fluid domain, right? It spits out some information here, and then it loads some information about the wall mesh, right? And then it says that the mesh data is imported successfully. Then it loads it about the solver parameters. It does domain decomposition using parameters because we're using MPI based decomposition. It's an MPI run. And then some other information about the phases on both the fluid and the solid domain. And then finally you have these numbers here. So basically you have it's because we are coupling these two equations. So it tries to make sure that both these equations within a time step, it solves for the FSI system, then it solves for the mesh system. So you have this alternate thing going on. If you don't couple them, then what it does is it first solves for the FSI system, lets it converge, and then goes to the mesh equation. So this is the strong coupling and loose coupling approaches. Now, here there are some numbers. So initially you have the time step and the nonlinear control, nonlinear step here. There's a 1, 2, 3, 4. Then this column represents the time taken, time elapsed with it for each time step. And then, so this one represents the nonlinear or Newton solver convergence. So for instance, ROA over R1 is the ratio of the current residue to that of the residue at the beginning of the nonlinear iterations. Ri over R0 represents the current residue ratio to that of the initial residue. And this one represents how the solver has converged. The linear solver has converged within the same iteration. So the linear solver's convergence is pretty good. So these are the total number of linear solver iterations. dB is like a decibel reduction. It kind of tries to compute the change in the residue in terms of a log value. And this is the total amount of time that it spends in the linear solver. So this is going to take some time. So FSI simulations are usually expensive. So I'm going to kill this run. It's going to continue and then open up a file that I've already pre-ran the simulation. So okay, so this is a history.file file. So you can see that the same thing continues, and it will take about maybe around 10 minutes or 20 minutes or so to finish the simulation. What I can do is show you the animation. So we can now load a ParaView, and within ParaView, I'm going to load the state file here. Open the results from the previously computed VTU files. So once you load them, you can do a variety of plots here. So here I'm showing the displacement plot in the deformed configuration in the 3D on the top left, and the axial slice of the domain in the bottom left. And then on the top right, you can see the axial pressure along the center line, and the velocity along the center line of the tube, and the outer wall displacement here.
Vijay, can I ask a question? Can I ask a question, or should I just wait till the end?
Yes, yes.
Did you say that you opened up a PVSM file? Was that generated by svFSI, or is that something you had already?
Yeah, so this is a PVSM file that I imported into ParaView. But the
Okay.
results are from svFSI, the VTO file.
Okay, that makes sense.
Okay. So then you can actually play this video. I've amplified the displacement for visualization. I've scaled up the displacement by a factor of 5, but you can quickly see how the deformation as the pressure pulse goes from the inlet to the outlet. You can see that this is the pressure pulse going through, and then you can see how the deformation happens with the pipe. Okay. So again, before closing this session, I just wanted to allude you to another quick thing. So svFSI also allows you to do a pre-stress based simulation of FSI, which I probably try to cover in the next video. So basically, it's kind of very similar to the FSI that we just demonstrated. However, the pre-stress approach needs a proper workflow. So there, what you have to do is like do initially a rigid wall simulation, just like how you do it for CMM based wall deformable wall simulations in SVSolver. And then you compute a rigid wall mean pressure or traction, and then go into the deformable wall simulation. So first you have to pre-stress it. So here is a simple, so this is a rigid wall simulation here. So so basically, again, general parameters are very similar to the FSI. Here you only load the fluid mesh, and you're solving for the fluid equation here. So we try to use bipartition method, which is optimized for fluid simulation. So we use that as a linear solver. Other than that, remaining all of the same predictions as that of the FSI. So it's a steady inflow. Instead of a pressure pulse providing at the inflow, here we are providing flow rate. It's a dirichlet boundary condition at the inflow, and we provide RCR. So here is the RCR, where you can input RCR boundary condition in the svFSI, where you provide RCR values as proximal resistance, capacitance, and distal resistance. So you do this rigid wall simulation. And here is, I think, how the output looks like, very similar to the FSI case. So once you're done, then you do the pre-stress simulation. So for pre-stress, what you have to do is like, again, load the wall mesh, very similar to the FSI case. However, here you solve for struct directly. Instead of doing FSI, you solve for struct. And here you have to set the flag that you are doing the pre-stress. And when you pre-stress, the code expects you to provide material properties of the solid. And then the code expects you to provide, let's say on the wall, on the inner wall, you provide the pressure, the pressure field that you got from the flow, from the rigid wall flow simulation. You can either provide a VTP file here for pressure or a traction, and then you let this pre-stress go on. So once you do that, you can see here the pre-stress simulation output file. So where it kind of also provides you a norm of the displacement. So as it is pre-stressing, you will find that displacement actually comes down. So once it converges to, let's say, the total norm of the displacement is of the order of 10 to the power of -5. So we started off from, let's say, 0.1. So we're happy with this. So now what you can do then is do a pre-stress based FSI, which is kind of very similar to the other FSI. So I'm going to load this input file here. So what happens here is you can now, you can load the lumen data, that is the fluid data, but you can also initialize the flow field using the rigid wall simulation for your FSI. So all your rigid wall simulation that you did initially, so you can load the velocity and pressure field and initialize your fluid domain for the FSI simulation. Then for the wall, you can provide the pre-stress part. So the pre-stress as well as the initial displacements, you can load it from your pre-stress simulation for the wall, and then do the projection just like how we did earlier. And then restore is just the same. So this way, this kind of workflow where you initially do a rigid wall simulation, then pre-stress the wall using rigid wall traction, and then do a pre-stress based FSI. So this lets you, this is the workflow that we typically follow for doing blood flow simulations, FSI simulations in cardiovascular situations. So yeah, so with that, I'm going to stop the recording. Stop the screen sharing and stop recording.